Welcome everyone. My name is Ben Consolvo and I'm an AI engineer at AMD. So unfortunately, Daron's not able to join me today, but I'm happy to give you this talk and show you some of the internal workings of a cloud-native preventative healthcare system. So all the way from the hardware to the model deployment, the infrastructure, and then to a front-end UI. So if you're thinking of taking notes, just know that all these slides are posted on the sketch.com website. So, if you want to stick around and ask questions afterward, that's great. But feel free to use those slides, the PDF of these slides on there. And also stick around to the end of the talk because I have some free AMD cloud credits for our GPUs. So you can take advantage of that. So healthcare organizations need to reach thousands of patients for preventative screenings, but manual outreach often doesn't scale, and automation lacks personalization sometimes. And so the solution that I built was building an agentic AI system to generate patient-specific criteria with the help of a screening prompt, so typing in a prompt and then looking at a patient database, and ultimately to write these outreach emails to suggest to patients that they schedule a screening. So here I'm using a cloud-native stack to build the back-end model deployment that's secure and can sit on the hardware of your choosing, whether you have like an on-prem cluster or you want to deploy it on the cloud. Either way, it sits on your own infrastructure and all the services would sit there. So I want to go over the hardware stack, the full software and hardware stack. So from hardware to healthcare, the software stack is entirely open source. The hardware that I tested was the AMD APISIX CPUs, Intel Xeon CPUs, and Intel Gaudi accelerators. The orchestration is done with Kubernetes and Helm charts for declarative deployment. And APISIX provides the API gateway, authentication, traffic management. Prometheus monitors all the inference endpoints, and then Grafana pulls that data from Prometheus for monitoring. And then AutoGen is a Microsoft open source framework that's for agentic AI, if you're not familiar with it. And it's what's used to define the actual screening criteria, filter the patient records, and generate those personalized emails. And then finally, on the front end is a Streamlit application hosted on Hugging Face CPU. But you could host this locally or wherever you'd like. So it's a fully cloud-native open source stack that any healthcare organization could deploy. So the main inference script is just inference stack deploy.sh. It's a bash script and sets everything up according to the config, which I'll briefly go over. Near the bottom of my slides, I point to the source in the GitHub repo where you can find what I'm talking about if you want to look at it later. So the main components of the deployment bash script are setting up the Kubernetes cluster and the config, the NGINX controller as the foundation to APISIX, Keycloak and APISIX setup with Ansible, and then using VLLM for inference for the LLMs. And then observability with Prometheus and Grafana. Then the application layer on the front end is set up separately from the deployment script because it's actually using the OpenAI API endpoint. It's pulling from that deployment, the backend deployment. So this is just an example or part of an example of a deployment configuration file, and apart from just some beginning kind of admin parameters, you just kind of set on or off on what you want to deploy. So after declaring some of those administrative variables, we are looking at, at the bottom of that script, deploy Kubernetes fresh on, so deploying the Kubernetes server, the NGINX controller, the Keycloak for authentication, APISIX, API gateway, built on top, like I said, of NGINX. And then you have your observability and deploying the LLM models, like I said, with VLLM. So I did also on the right-hand side show the current models supported, but you can also bring in your own Hugging Face model. These are just the ones that kind of out of the box we know work on all these that we know that we've tested. But yeah, you can pull in any other Hugging Face model as well. There's an API for that. So as I mentioned, the hardware starting at the bottom is native for both AMD and Intel, at least tested so far. It should work really on any data center hardware. Haven't yet tested it on the Instinct GPU, but I've tested it on the APISIX CPU, Xeon CPU, and the Gaudi machines. So yeah, I've yet to hook it up to ROCm and test it on AMD GPUs, but it shouldn't be too much of a leap to make it work there also. So now I briefly want to show you the Kubernetes dashboard. You might be familiar with this, you might not be. It is automatically deployed when the inference deployment script is run. So here's just a screenshot, but I will walk through a short demo video rather than doing a live demo showing how I pulled it up after deployment. All right. So yeah, the text is a bit small, but first I'm just looking for the deployed dashboard and then doing port forwarding to make it available on our local web browser. I expose the port in my IDE and VS Code. And then I need to create a, so yeah, we visit the URL here that's hosted through this Kubernetes cluster, and we need to make a service account and a cluster role binding for generating the token that it's asking for. So yeah, that's what I'm doing here. And then once we get the actual token, we can copy paste it back in and do all of our Kubernetes monitoring right from the dashboard. So I'm pasting that token in, and then yeah, here's our Kubernetes dashboard. It's really the equivalent of doing kubectl commands from the command line, but just in a dashboard form, and you can kind of view everything quickly without having to type in the commands all the time. Yeah, so that's the dashboard, and it should show all the resources in your cluster there. First, for those who are not familiar with APISIX and NGINX, APISIX is a cloud-native API gateway handling API traffic, providing caching, authentication, enabling efficient and secure access to deployed AI models. And then NGINX is serving as a foundation for APISIX, has high-performance proxy and load balancer for traffic, responsible for routing incoming requests, and ensuring access to deployed AI models. So APISIX transforms chaotic AI model access into enterprise-grade API management. So think of APISIX as the intelligent traffic controller for your AI infrastructure. So now let's dig a little bit deeper into APISIX or API Gateway. So like I mentioned, it's built on top of NGINX and uses etcd for configuration storage. It makes it truly cloud native and dynamically configurable. This very brief code snippet I'm showing is part of a Helm chart configuration, and it shows we're running 3 replicas of APISIX for high availability with the ingress controller enabled to automatically manage the Kubernetes resources. APISIX gives us advanced features like rate limiting, circuit breaking, authentication, and request transformation, all configured as plugins that can either be enabled or disabled. So VLLM, if you're unfamiliar with it, is an open source library optimized for high throughput LLM inference on data center hardware, both on CPUs and GPUs. So let's dive a little bit into how we actually deploy these models. This is the Helm command, this Helm upgrade install command that you see, that deploys, in this case, a Llama 3.1 8 billion instruct model to our Kubernetes cluster. So this Helm command abstracts away all the complexity of creating Kubernetes deployments, services, config maps, and secrets. So one command really deploys the whole model endpoint. And you can actually, midway through your deployment, you can provide this Helm upgrade command again if you wanted to change something without having to redeploy your whole cluster. The Hugging Face token allows us to download the model from the Hugging Face hub directly into the cluster. A couple key parameters here are enabling both the APISIX integration and the Prometheus monitoring. And the CPU equals 96 is we're allocating 96 CPU cores, and then we're allocating 256 gigabytes of memory. Remember, these CPUs have quite a large memory footprint. Using tensor parallelism with size 2 to split the model across 2 NUMA nodes, in this case. And then the force command will delete and recreate resources, if you want to include that, each time the command is run. All right, so here's what makes this deployment unique. The VLM configuration optimized. In this case, it's for x86 CPUs. So the 40 here, the VLM CPU KV cache space, means that we can run more. This is for 40 gigabytes and for the KV cache, and we can run more requests in parallel when we have a bigger cache. And the VLM CPU SGL kernel equals 1 means that we're using a small batch optimized kernels for low latency requirements like online serving. And then below that, the extra command args, that model config section shows Llama 3.1 specific settings, or specific model settings. So we're using bfloat 16 precision to reduce our memory footprint while maintaining our accuracy, and setting a max sequence length of 8,192 tokens and using multiprocessing as the distributed backend. The chunked prefill feature allows VLLM to process long prompts more efficiently by breaking them into chunks. And we're batching up to 2,048 tokens. So the beauty of Helm is that we can customize these values at deployment time or use the model-specific defaults. So moving up the stack, let's look at observability. Observability is critical when you're running production AI inference. You need to know what's happening inside your models and your cluster. So we use the standard Prometheus plus Grafana stack, and Prometheus scrapes metrics from our VLLM endpoints, things like request latency, token generation rate, queue depth, memory usage, CPU utilization. So these metrics are stored in Prometheus's time series database and evaluated against alerting rules. So if something goes wrong, say if token generation latency exceeds 2 seconds, or if the error rates spike, you can have it ping your Slack or send you an email, or whatever alerting mechanism you choose. And then Grafana provides the visualization layer, so you can build custom dashboards to monitor things like real-time request rate, model-specific metrics like tokens per second, resource utilization across the cluster. And here is an example of a model dashboard. I know the text is a bit small, but this is kind of what it might look like, where you can see things from the time series database, like end-to-end request latency, token throughput, time to first token, time per output token, cache utilization, even prompt length. So it's a great way to be able to observe what's going on in your cluster. All right, so now moving on to the application layer, the UI on the front end. So like I mentioned, using a combination of AutoGen for the Agentic framework from Microsoft, Hugging Face for the hosting the actual front end, and then Streamlit is the front end UI. So this application uses natural language understanding from prompts for the agents on how to act. And it uses an OpenAI compatible API endpoint that I mentioned was deployed with the backend infrastructure. And you can take a tour of the application yourself, actually, by visiting the app, because it's hosted on Hugging Face's CPU. I have it hosted on my own spaces there. Yeah, you should be able to just search for it too, Preventative Healthcare, Consolvo, and be able to find it and try it out yourself. So here I just want to show you a short video demo, again, of the front-end application that I built. So it is a multi-agent system that uses natural language prompts for each of the agents. So there's an agent for the user that represents the user. There's an agent for the epidemiologist, which decides which patients to target for screenings. There's a doctor critic agent to review the epidemiologist's suggestions. And then there's finally a LLM to write some draft emails for the patients. So then when we scroll down from there on the left-hand panel, we have like our sample data set. It's a synthetically generated data set, but you could use your own data set or hook in your own database. And then you provide some kind of screening prompts, like here I have breast cancer screening, and then, yeah, we can put in some contact information for the email at the bottom. And then, yeah, here on the right, it's showing a log of what's happening in the interaction between the agents, and then generates these emails that are essentially like drafts of emails. I wouldn't recommend just blindly sending out these emails, but it provides pretty good drafts of emails, and it has looked at the patient data, both the descriptive data as well as like gender, age, to decide which patients to reach out to. So, and then yeah, here I'm just showing kind of a README that if you wanted to get this set up yourself, you could walk through some of the steps here. But the simplest thing would probably just be to clone this Hugging Face space, and then try it yourself. All right. So what did we create? We connected the dots between a useful application for healthcare and a robust cloud-native stack for model deployment. We built an agentic framework with Microsoft's AutoGen to save countless hours of patient selection and manual outreach for preventative healthcare screenings. The backend infrastructure is completely open source, from the Kubernetes orchestration, the VLLM model serving, to the observability with Prometheus. Open source models like Llama 3 and DeepSeek R1 distilled are models that anybody can use, or you can host your own closed source model or one that you've fine-tuned for your use case. So let's talk about business impact, because that's what healthcare organizations care about. First, clinician time. So this should free up clinical staff to actually see patients, their core job. The preventative screenings might include things like colonoscopies, cardiovascular assessments, mammograms, et cetera. These comprehensive preventative care becomes more feasible when you have, like I said, thousands of patients. So the cost is a big factor in any model deployment. This can run on both commodity x86 CPUs that you might already have, as well as GPUs. So the entire stack, like I mentioned many times, is open source. So all the parts of it, and there's no per token API fees, because you're hosting all the infrastructure yourself. No vendor lock-in, no surprise bills from OpenAI or Anthropic. All right, so if you want to get started, like I mentioned, you can actually visit the application itself that I've hosted on Hugging Face. And then the enterprise inference stack that I went over, the whole backend, that's also available on GitHub, so that second link. And then here I just wanted to let you go ahead and try AMD's latest Instinct GPUs on the AMD Developer Cloud. So this QR code is good for $100 in cloud credits. So you can feel free to take a snap of that and use that, or like I said, you can visit these slides afterward and find the same link there. Yeah, so that's all for my talk, and appreciate your time. If you have any questions, I'd be glad for you to come to the microphone there.
Hi, my name's Jonathan. I too work in heavily regulated industries, and some of the feedback that I've gotten from my stakeholders have been concerns around the long-term maintenance of a full-on open source stack. We definitely want to avoid vendor lock-in, but at the same time, in a lot of cases, there's a lot of overhead associated with maintaining something on your own, and particularly in organizations that don't have the depth of skill set in this area. What sort of feedback did you get in general as far as the long-term maintenance and support of some of these tools, particularly around Keycloak as well, which is so core for IAM?
Yeah, no, I haven't actually personally gotten feedback on that yet, but I guess just taking a stab at it, yeah, there's often times where you need to customize and build something that is a little bit more tailored to the organization, and then maintain that yourself, or yeah, hire a contractor if you're a health organization to kind of maintain that stack. But
Gotcha.
yeah.
Thanks.
Yeah.
Hello.
Hi.
As far as the patient interaction, what types of things did you use to kind of verify that it was giving information that is acceptable? Like patient safety, especially in healthcare, is a huge issue and concern. So, like, was there anything that you did in that space?
Yeah, so I did find, especially with these LLMs at first, that there were a lot of hallucination and strange things that it was coming up with, and had to put some guardrails and some tooling to ensure that the output was appropriate and suitable, and not coming out with a range of just stuff that it shouldn't. So I put some pretty tight guardrails on what the output of the email should be, and really restricted it a lot with tool calling, specific tool calling to make sure that it wasn't coming out with some hallucinations.
Did you use anything to observe as well? Like
Any what? Sorry.
Like to observe it. Like, let's say, you've tested it and feel that's good, but then when it's out in the wild, right? How do you ensure that it's continuing to behave as expected?
Yeah, no, I didn't have anything on follow up on that front, but yeah, that would be definitely helpful.
Thank you.
Yeah.